Hey everyone, and welcome back to The Explainer. Today, we are diving into what I can only describe as an absolute masterclass in aerospace meta-engineering. We're breaking down a seriously brilliant blueprint that takes the wildly complex evolution of rocket nozzles and somehow structures it all into a clear, totally compelling narrative. Let's jump right in. So, picture this. How on earth do you revolutionize rocket design in just 15 steps? Sounds kind of impossible, right? Transitioning from conventional manufacturing to cutting-edge additive manufacturing is a massive, massive leap. But the source material we're unpacking today proposes exactly that. It gives us a comprehensive architecture that maps out this entire innovation shift without cramming or overwhelming you. It's just a perfect exercise in structural brevity. Here is our game plan for today. We'll hit 1. The rocket nozzle problem. 2. The additive manufacturing shift. 3. Materials and DFAM principles. 4. A real-world precedent featuring ISRO. 5. Blueprinting the original design. And 6. Advantages and limitations. All right, kicking things off with Section 1, the rocket nozzle problem. Traditionally, building a rocket nozzle is, well, actually, scratch that. It's not just building. It's an exercise in extreme friction. You're dealing with ridiculously complex parts, intricate welds, and lead times that just drag on forever. And remember, every single weld is a potential point of failure under immense stress. But additive manufacturing, it completely flips the script. It unlocks this incredible design freedom, letting us integrate intricate cooling channels directly into the structure and achieve massive part consolidation. The old way is hitting a brick wall, and the new way just shatters it. Which brings us nicely to Section 2, the additive manufacturing shift. At the very heart of this aerospace revolution is powder bed fusion. Now, this isn't your basic desktop 3D printing extrusion. No way. This is a highly advanced process where a laser or an electron beam selectively melts incredibly fine layers of metal powder together, just one microscopic slice at a time. It's the fundamental capability at the core of our source material, and it allows engineers to build these high-performance, heat-resistant rocket nozzle components literally from the ground up.
Moving right along to Section 3, Materials and DFAM Principles.
You can't just hit print on a rocket using any random metal you have lying around. The blueprint specifically targets the heavy hitters, alloys like Inconel 718 and 625 for extreme high-temperature strength, GRCOP 42 and 84 for unbelievable thermal conductivity, and C103 for the most extreme environments imaginable. But the real genius here is the design rationale. Engineers can't just pick an exotic metal because it sounds cool. They have to explicitly defend exactly why it fits their specific design constraints. Because, look, additive manufacturing offers immense freedom for sure, but it still has to obey physics. Enter design for additive manufacturing, or DFAM. Engineers have to strictly calculate minimum wall thicknesses, carefully manage overhangs so the structure doesn't just collapse on itself, and map out really precise support strategies. If you ignore these critical constraints when you're building in 3 dimensions out of molten metal powder, yeah, your print is going to fail long before it ever sees a test stand.
Okay, Section 4, Real-World Precedent. Let's talk about ISRO.
Any bulletproof engineering proposal needs a solid anchor in reality, and the blueprint brilliantly leverages the ISRO PS4 3D printed engine as its case study. By pointing to a proven, real-world success with hard numbers, it shifts the audience's mindset right away from, oh, that's a cool idea, to, wow, this is a proven capability. That lends immediate, undeniable credibility to the original designs we're about to look at.
Which takes us to Section 5, Blueprinting the Original Design. The design work here follows a beautifully structured 4-step sequence. Step 1 lays the groundwork with your assumptions, stuff like chamber pressure and thrust targets. Step 2 crunches the sizing math for expansion ratios, physical dimensions, and the precise nozzle contour. Step 3 visualizes the CAD geometry and really highlights those intricate cooling channel layouts we talked about earlier. And finally, Step 4 validates the whole design through intense thermal and structural analysis. This sequence is just textbook on how to flawlessly guide an audience from raw mathematical assumptions straight through to a validated structural outcome.
Finally, we arrive at Section 6, Advantages and Limitations. Let's be real, a solid engineering pitch has to own its limitations just as heavily as it hypes its advantages. We have to weigh the absolute flawless production potential of additive manufacturing against the harsh, unforgiving technical realities. We're talking warping, defective prints, and hidden potential failure points. Truly understanding those risks, the material limits, and the exact challenges of rolling this technology out on a massive production scale, well, that's the hallmark of real engineering maturity. So,
To wrap this all up, if a revolution in something as wildly complex as rocket nozzle engineering can be comprehensively structured, argued, and proven in just 15 precise steps, what other massive aerospace challenges are out there just waiting to be blueprinted? The true power of this source material is proving that with the right framework, even the most daunting technological leaps become incredibly logical and totally accessible. Thank you so much for joining me to dissect this fascinating engineering architecture today. Keep learning, keep questioning, and I will see you in the next explainer.